would like to introduce Anish Shaikh, who will be presenting experience and observations in deploying cloud-scale routing security. Anish is a principal engineer at Google and traveled from the San Francisco Bay Area to join us today. This is Anish's fifth time presenting at NANOG, and his first talk at NANOG was called SDN in the Management Plane, Open Config and Streaming Telemetry. This was back at NANOG 64 in San Francisco 2015. Welcome back, Anish. It's a pleasure to have you back with us again.
Thank you, Michael. It's great to be back at NANOG. We have an intimate setting today, so looking forward to the discussion and questions. And of course, please feel free to talk to me offline afterward. We gave a talk a few NANOGs ago on basically this notion of needing to have multiple layers when trying to attack the problem of routing security in the internet. There's no one single silver bullet, as all of you who work in this space know. So this time, I wanted to give a little bit more detail and some learnings after going at this for a few years at Google and deploying these services for filtering and other parts of the solution at cloud scale. And it's my privilege to give this talk on behalf of a lot of other teams that have worked on this with me, our software teams, our SRE teams, as well as the teams that manage our peering relationships with external networks. Okay, let me set some context first on Google's network. Since the early days of Google's inception, we've been investing a lot in our own network infrastructure. Right now, we're up to the numbers that you see here. We run a global backbone today with maybe the most relevant statistic for this talk is the number of external edge locations that we connect to other networks with, and of course connectivity around the world. We have quite a bit of both subsea cables and lit fiber, as well as cloud regions and edge POP locations. Now, if we zoom in a little bit more into the focus here, which is on routing security from Google's perspective, the way we connect to the rest of the internet is a few different variations. So we run a private WAN effectively, where we host both first-party applications. These are the things that many of us use: search, mail, maps, photos, all of those services, as well as our Google Cloud Platform, which is basically where we allow third parties to come and host their applications on our network. And we connect to the rest of the world a few different ways, obviously through other large ISPs, broadband networks that provide connectivity from users to our services. Transit providers, we use a few transit providers in some locations for resilience primarily. And then we have customer networks that connect directly to us. So these might be enterprise networks that either peer with us directly or peer via specific providers that we help identify. I'll talk a little bit more about the VPP program towards the end. And then we also have private connections that aren't publicly routed. We call this variant Cloud Interconnect at Google. Other cloud providers have very similar services. Now, from the perspective of the rest of the internet, Google looks like a stub network in that we don't really provide transit for other networks. But it has some unique characteristics. The first of which is that we have a very large peering surface, right? We have thousands of peers, and that gives us effectively independent reachability to a significant portion of the rest of the network. So we have, maybe one-hop connectivity to a good deal of the rest of the internet. We also have a global presence, as I mentioned before. We peer in both private facilities like colos, as well as in many exchange points around the world. And as I mentioned, we do use transit connectivity, but it's primarily just for resilience. So we just have it in a few places, specifically for places where we might not have reachability to every single end user. And one more bit of background. From a cloud service provider perspective, there's a few different kinds of routes we care about protecting. Now, traditionally, at Google, the hijacks problem was about making sure that the routes that we announce for customers and users to reach our services, Gmail or search, etc., were protected. That was our problem for a long time in the BGP hijack space. Now, and of course, we also had the problem of the routes that we accept and needing to make sure that those were valid, because that's basically the return path to the users that are connecting to those services. With cloud, there's a few additional considerations that we have. One is that we now have to pay a lot of attention to the routes that we get that are to reach third-party services that our customers use. So this might be other CDNs, other clouds, obviously. Many of our customers are multi-cloud. Making sure that we have robust routing to those services is super important. And then the relatively newer problem of managing third-party routes. These are routes that customers bring to the cloud platform and are announced by Google. I'll say a little bit more about this bring your own IP variant in a bit. The other problem, I think, for cloud providers is that, unlike before, we have to pay a bit more attention to the routes themselves and kind of who they belong to, because unfortunately, not all routes are equal, in the sense that in addition to paying attention to things like how much traffic the routes carry, we also worry now about the type of the traffic on the route. So cloud customer traffic, for example, gets special attention. Routes associated with some critical services or some specific peers that might be considered high-value peers by various metrics that we use are also things that we pay a bit more attention to. So these are kind of some of the considerations that are, a bit, again, specific to cloud service providers, maybe in contrast to ISPs. Now, with that bit of background, I wanted to talk a little bit in this section about how we've architected and deployed our services for route filtering, specifically for high availability and resilience. And we tried to approach this in the same way that we have built all of Google's software services, really. In other words, looking at them the same way as we build other distributed services and use the same techniques that we use for those services to ensure their reliability and scale. So I just wanted to mention a few of the key principles that we use that have been specifically important for the route filtering problem. One is regionalization and replication. So this really refers to the idea that we want to make sure that the services we deploy are sharded so that each individual instance of the service only manages a portion of something, whether it's a portion of the network, a portion of the address space. I'll show you what the sharding strategies look like for the filtering solutions. But that's a general idea, and the whole objective is to make sure that we don't have a single instance causing a multi-region or global failure. So this is the point of regionalization of services. The second is around progressive rollouts. This basically just means that when we roll out a new version of code or configuration, we do it progressively. So it's not that we update all of the instances at once. We use strategies like canarying, where we deploy it to maybe one instance in one metro, for example, run a bunch of tests, health checks, etc., and then we progress the rollout as we pass those tests, so that it takes some time to roll out the entirety of the service to the fleet, especially when we're talking about our edge fleet, thousands of devices if we need to actually touch our devices, or many edge regions where we need to roll out the services. And so we use the progressive rollouts to achieve that safely. And then finally, this idea of defense in depth. So this is really about safety checks that we use at multiple layers. So here, we use techniques like checking inputs before we deploy or before we activate a service, doing impact analysis. So in the context of route filtering, that might mean looking at which routes will be impacted by a particular change, whether it's to code or configuration. And also, as we do a rollout, we rely heavily on real-time checks. So when we update something, we do some set of health checks to make sure that we haven't broken it. And then if we have detected something, then we sort of roll back. So this notion of multiple layers of safety checks, some of them might be redundant, but we embrace this idea of defense in depth. And as I said, we've tried to apply these principles across the board in our routing security implementations. So let's look at some examples of that. We'll start with the IRR filtering pipeline. This is where we started our work on employing routing security. When we started this effort, RPKI was relatively still, I would say, adoption was kind of low. You might even call it nascent. I think it's not, as we've seen in the last few years, a rapid increase in adoption. So we decided to start with IRR filtering first. And at a high level, what we're doing is basically generating an IRR filter or prefix list for every one of our peers using public databases, and then rolling that out periodically to the network. So the pipeline looks as shown here. We use the public IRR databases. We still use too many of them, in my opinion, but we use a bunch of them. We collect snapshots periodically, multiple times a day. we have a service called the route intent store that basically analyzes all of the route objects that we collect, as set objects, route objects, sources like peering DB, for example, puts all of that together and builds a list of what prefixes we expect to receive from any given peer. And then we use that service as a source for the filter generator. So the filter generator runs periodically, consults the intent store, and generates a filter that then is subjected to a bunch of safety checks that I'll describe in a second. And then we produce a versioned instance of the filter as an archive. And then that archive is picked up each rollout period and rolled out to the network. So if we look at the kind of checks we use here, first of all, we apply this replication principle. All of the services are redundant in the sense that we have multiple replicas running. At Google, we have services that run in our clusters. Clusters might get drained for some reason. Services might get ejected or deactivated for some reason. So tasks and jobs are constantly changing. So we always have to deploy things redundantly, so we have multiple instances running at any given time. The second is this notion of pre-deployment and real-time safety checks. So again, the defense in depth idea. So when we generate a new filter, we run a number of safety checks, which I'll describe. And then we also run checks as we deploy the filter to the network. So in other words, we check the health of the metro, for example, after we make a change to the devices there. And the progressive rollout means that it does take us several days to roll out a full set of filters to 1,000 devices or thousands of devices. We start on roughly the beginning of the week, and roughly midweek is when we finish. So that means that there is some delay. This is one of the maybe trade-offs with progressive rollouts, is that you can't instantly update. And from the routing perspective, if it changes routing, there's some churn during that time as we roll out. But generally, this hasn't been a major issue for us. Okay, so let's look at the RPKI pipeline, and then we'll come back to the safety check specifically. So with RPKI, we've also deployed a large software system for our origin validation solution. So we have our relying party software. We use RouteNator, multiple replicas running. When we pull down VRPs or ROAs from the various trust anchors, we analyze them and put them into our own RPKI cache, which produces an updated version of the RPKI cache. Think of it as a validated snapshot of the RPKI contents at not any point in time, whenever it runs, or periodically. So there is some delay. It's not sort of instantaneous, and I'll say more about why we do it that way. Then we have a pusher job, basically, that picks up the archive or the set of validated VRPs and pushes them out to a fleet of validators that are sharded by region in the network. So each region has its own dedicated set of validators that looks at the routes that we receive externally in that region through a set of route collectors that are deployed there, and then makes decisions on whether those routes are valid or not based on the contents of the RPKI cache. And if it finds an invalid route, it uses our standard config push mechanism to actuate or install filters on the devices. And similarly, it'll remove filters when routes either become valid or we detect that we're no longer receiving an invalid route from that peer. So it's a little bit different than the standard RTR RPKI implementation that many use in the industry. And we have our reasons for that. Please feel free to ask me about it offline. I won't cover that today, but happy to talk about that. So similar thing here, we have a few different techniques that we use. Again, replication, obviously. In addition, though, we also have, you can see that the validators themselves are sharded. So they only are responsible for the set of routes, or the set of routers, I should say, that receive external routes in that specific region. And by using progressive rollouts across the validator fleet, we can make sure that, let's say, the contents of a new set of VRPs in the RPKI doesn't break anything unexpectedly as we roll out. And of course, we have the pre-deployment safety checks as well. In other words, we do an impact analysis every time we publish a new version of the RPKI cache. For example, we look specifically for routes that were valid before that now became invalid. And then we may actually decide not to update the cache for that reason until we can see what happened there. Okay, let me talk a little bit about the safety checks specifically. So on the IRR side, one thing we did, since this was our first foray into route filtering, was that we did a fairly progressive or a gradual introduction of IRR filtering. We started just by marking routes that looked invalid according to the IRR. And the point here was really just to start, hardening the pipeline that we have overall, tuning some of the safety checks, and also using it as an opportunity to communicate with all of our peers that, hey, we're about to start filtering. Just be aware that these are the set of invalid routes we're receiving from you. We updated our peering portal to communicate this to our peers. Then instead of going straight to rejecting the invalid routes, we went to depref mode, which has the effect, the intended effect of basically moving traffic off of direct paths onto maybe indirect or transit paths, in the hopes that it would spur operators to notice and then fix their IRR data, so that we improved the overall quality of the IRR in the process. I would say we had some success, but probably modest in this effort. And then finally, once we've built up enough confidence, we've communicated multiple times with our peers, we switch to reject. And this is the place where we actually get some protection from this kind of filtering. With depref, of course, you can still suffer a hijack, especially with things like sub-prefix hijacks. Doesn't help you there. Now, in terms of safety checks, we have a few different things that we do. When we have that new candidate filter set that I mentioned, we have safety checks that are trying to do two specific things. One is to prevent peering link congestion and impact to paths. And this was specific to the time when we both depref and reject modes. So, and the second goal is basically to detect whether by adding a filter for a particular prefix, we've created a potential black hole. Like if we don't see an alternate path to that route, that's something else we check for. And then I won't say a lot, but we have real-time checks, as I mentioned, during the rollout itself that checks the overall health. These are somewhat generic checks that we run for lots of different kinds of rollouts that we would do. So the traffic safety service is our safety checking for IRR. It takes a few different inputs. It takes a new version of the filter set that was generated by the intent store and filter generator. It takes traffic volume statistics that we have on a per peer, per prefix level. So in other words, how much traffic is being carried by this route from that peer across our network. And it takes a set of the routes themselves that we're getting at any point in time from a peer. And then it looks basically two different things. The traffic shift check checks that if we were to invalidate some set of routes in the current prefix list, how much traffic might actually move? What's the risk of congestion? We look at some thresholds that we have to make sure that we're not shifting more traffic than expected or that we might think is safe. Now, those of you that run large networks know that there's constant churn at the edge of the network. I mean, there's traffic moving around all the time. So it took some tuning to get these to be useful and not create lots of false positives as well. And the alternate route check, of course, does what you'd expect. It makes sure that we have an alternate path to reach a prefix if it's deemed invalid in the prefix list. And if the checks both pass, we go ahead and update the new filter content and roll it out to the network in the next rollout period. And if they fail, we fall back to the previous filter for that specific peer. So for each peer that doesn't pass the safety check, we'll use the previous version, and then we'll create a ticket and sort of try to communicate with the peer and see if we can get it fixed. So this is kind of the safety check approach that we've taken. Now for RPKI, we have a slightly different approach. Thankfully, these aren't work in progress anymore. These are all done. Validation of the public RPKI data. Now I mentioned before that we don't just directly use the data that gets pulled down via RouteNator. We've found that using data directly from external sources has its own risks, specifically that things change dramatically there, and it could cause a major problem if we just start using it. So instead, we've employed this approach of periodic releases of the public RPKI data. So we have version releases of the data that goes into the network that's based on what comes from the public data sources, but it's not at any point in time directly reflecting, which means, of course, that there is some delay between the time that an update happens in the RPKI and that it shows up in our network. And we validate each release through some very simple checks, basically, looking for significant changes in the number of VRPs in each release, and also doing that impact analysis on the reachability, specifically looking for routes that change their validity from valid to invalid specifically. Then we do a bunch of reliability checks also when we look at the RPKI cache. So this is similar to the alternate route check that we do for IRR. We particularly look for cases where we might black hole a route that's invalid. And our starting point was that we basically would provide a way to override the RPKI if we detected that there's a black hole potential. I mean, there are some routes, I was surprised actually, not a huge number, relatively speaking, but it's not tiny either, that we don't actually receive them over transit either. So if we were to count them as invalid, there's no actual way to reach that prefix. So then we're developing also policies to say, can we automate the override process as well? If there's not that much traffic or we haven't seen any traffic, which is true for some of those prefixes, we can just go ahead and filter it. And then we built a bunch of tooling to enable overrides and escalations. So you could turn off filtering for a given peer. We expect, especially for cloud customers, to get some level of escalations. Fortunately, we haven't had to use this too often. But we do have the ability to, at a relatively fine grain, allow certain prefixes or prefix origin pairs from specific peers. Now, despite all of these safety checks and things, it hasn't been without its own challenges, and we have had some. So these are some examples of incidents that we've still experienced despite our best efforts. The first one is around some high-value peers that actually lost connectivity after we introduced IRR filtering. Some of these were due to what I would call brittle routing architecture. These are cases that were interesting where the provider of the customer is advertising an aggregate that includes the routes that that customer has, but the customer themselves aren't advertising reachability to their provider. So it looks to us like there is a path to get to that route if we were to filter it, but there actually isn't. So when we send traffic that way, it just got black-holed. That's one. The second, with that same customer, they didn't have redundant route announcements from different points in the network, and both of the routes that they announced to us were invalid in the IRR. They didn't actually know what IRR was, so we had to kind of help them remediate that problem directly. The other one that's risky here is that I think that when we try to automate impact analysis for filtering, sometimes we use rules that are overly simplistic. For example, traffic related. Sometimes even a small volume of traffic can be critical, and we introduced filtering and said, this is going to be invalid, but it's okay because it's very little traffic. It turns out that that traffic was pretty important, so we had to roll that back. And there's a few other cases. I won't have time to go through all of them. There are cases where the IRR was defeated by our own algorithm in how we expand the set of AS sets or collect the set of AS route objects, rather. And we basically needed to update our algorithms in response to that. Or some cases where the IRR was just wrong and we had to say that they were resolved finally by moving to RPKI. One limitation of our IRR filtering is that these prefix lists can be really big. So we have a limit on how big a list we're willing to configure on our devices based on scale testing and so on that we did. Now, a filter list that's bigger than that, of course, means that we don't actually have a filter for them. So we basically have to rely on RPKI origin validation for those. RPKI origin validation only validates origin, so it doesn't do exactly the same thing as what IRR filtering does. But that was a limitation. So we did see some cases where there was a hijack from a network because we didn't actually have an IRR filter on them at all, because they're just too big if we expanded the AS set. Now, a few observations from the RPKI. We track who the sort of top senders are of invalids to our network. And I'm not putting these numbers here to don't focus too much on the specific networks, but the point of this is really two things. One is that we use this basically to go and directly talk to these networks to figure out what's going on in their RPKI. Why are they sending so many invalids? Can we help them to resolve them? The thing that I found interesting in this, though, is that if you compare the top 10 that we see and the numbers of invalids that we see with what's shown in the public routing tables, here the example is taken from NIST, which goes across both route views and RIPE, you can see that there's very little correlation, and the number is also very different. There's a bit of a, this snapshot was taken right at the end of January, so there's a bit of an anomaly. In general, the public routing tables only have about 5,000 invalids at any given time. It just so happens that there was a big jump in one of the networks recently. But you can see in this view, the red arrows here are just cases where there's actually a similar ASN in both our edge view as well as the public routing table view. And you can see that there's no similarity on the IPv4 side. In IPv6, there's just several of them. So the public data is very, I would say, non-indicative of what we see at our own edge. And initially, for a long time, this was largely because lots of networks will do their best to traffic engineer how traffic comes from Google, and they'll disaggregate their routes to us, and they'll try to advertise specific sub-prefixes, while their RPKI, of course, doesn't reflect that. And we've been actively communicating with all of these networks to try to help them resolve, but it's an interesting anomaly that we continue to see. The other interesting thing is that we see a frequently changing distribution of how many of these invalids are due to origin mismatch versus a max-len mismatch. And we have a small proportion that actually don't match in either one. Now, IRR filtering, just a couple words about this. As I said, we saw some modest improvements. This is a graph over time of the number of peer ASNs that had 0 invalids in their IRR. And you can see that there's some steady improvement over time that we got during the deprep phase. And fortunately, we had relatively few escalations, although they were certainly not 0. Our operations team did have to field them and work with us in the dev team to resolve them. And as I mentioned before, the fact that we have a limited size on how big a filter we'll deploy, it means that there are some gaps in our filtering. And interestingly, there's also some networks out there that create AS sets that are excessively large compared to the number of routes they actually send. This is probably not a surprise to many of you, but that means that we sort of artificially don't filter them for that reason. So we're looking at strategies where we might actually right-size their prefix lists based on what they actually send. But that has its own challenges, as you'd expect. We also definitely want to cut down on the set of IRR databases that we use, right? I think that we still have, I think, an overly permissive set that we draw from. There's proposals to only use, authenticated databases that are run by the regional registries. That would be a problem for us because we publish all of our routes in RADB, which now has better authentication as well. But we've done some experiments to see whether we could restrict the set of IRRs that we use. There is some impact, but it may be modest enough that we might actually start to be a little bit more strict about the set of IRRs that we will accept. Okay. In this section, I wanted to just touch on a few specific areas. One is bring your own IP. I think this is an interesting problem space. Since I'm getting close to being out of time, I'll just go quickly. The basic problem with bring your own IP is that the life cycle management of these addresses is a problem. In general, customers ensure that or prove the ownership of those addresses by creating a ROA that allows the cloud provider or Google to advertise routes on their behalf. Now the problem is during the decomp phase. So after that route gets provisioned, we validate that there's a ROA for it. In some cases, when the customer decides that they don't want to use the service anymore, they just delete the ROA. And of course, we don't really get a signal of that until our RPKI cache gets updated and so on. And we don't actually know if that's a signal that they've gone away. Did they make a mistake in their RPKI registration? What to do is not obvious. And so we spend a lot of time chasing after those customers to figure out what they actually wanted to do. That's one problem. The second is that just creating ROAs doesn't necessarily ensure that propagation of those routes works. We've had cases where networks have filtered the routes without a valid IRR object, for example. And many of those customers don't know what IRR is, don't create IRR objects, and we've had to resort to things like proxy IRR registrations, which we don't really like to do, but it's been required for some cases. I won't spend a lot of time on the route server decom project that we have. I would just say that we have decided to basically stop using route servers and IXPs primarily because of the security challenges that they present. There's a lot of challenges that we've had over a long time with them in terms of how we manage congestion, especially on the inbound direction. But really what got the business willing to go and take on this project and do this work was the fact that we can't really do filtering effectively on those routes. And we think that there's a significant risk in those places. So we've started that decom project. It's mostly completed at this point. Happy to chat offline more in detail with folks. And the last thing I'll say is that the challenge with enterprises connecting to Google directly over standard BGP peering is another challenge, right? That we have tried to come up with various mitigations for. There's a common issue. Customers expect an SLA on however they connect to us, but standard BGP peering at our edge doesn't really have an SLA or any uptime support guarantee. And customers in general aren't really able to, the same way that ISPs are able to manage redundancy in their connectivity, their advertisements, et cetera. So our preferred approach really going forward is this new product we've released called the Verified Peering Provider, where we sort of steer customers to use a set of providers that we've ensured and worked with to make sure that they meet our technical requirements on peering diversity, and they have a simple way to onboard customers from a connectivity perspective. And so far we have close to 20 of them with more of them coming. So I'll wrap up there. We've treated route filtering as a cloud-scale distributed software problem. And we've used the same kind of techniques that we use for other Google services in terms of multiple layers of checks, replication and regionalization, being really careful about use of external data. We found that having tools to mitigate issues like a big red button that just turns off filtering for a given peer have been really important for our SRE teams and operational teams. Route behavior at our edge looks very different than it looks elsewhere, and it's super dynamic. I think it's significantly different from what's seen in the public internet. That was an interesting discovery. And then this challenge of the mix of enterprise customers and route filtering has been a challenge, and it does require some special handling on our part. So with that, I'll stop there, and if there's time, happy to take any questions. Thank you so much.
Hi there, Aaron Atach, Akamai. Great talk. I noticed a couple things in your talk that I just wanted to see maybe if you could clarify. Specifically, you referenced some black holing for certain destinations depending on if filtering is implemented. I think what that effectively means is you're not accepting any external transit default route, and you're only accepting the more specifics. Is that true?
That is true. We don't have the equivalent of a default route. We only use the routes that we see from our transit providers. Yes, good observation. Thank you.
Second to that, for peers that you cannot implement filtering for prefixless on because they're just too large, are you implementing max prefix? Like a max prefix limit?
We do implement max prefix limits as well in the network. It's funny, we use the IRR to determine the prefix list size, and then we have some other heuristics that we use on a peer to determine max prefix. You could argue that those things should be normalized, or at least jointly planned, and right now they're not. So I think that's a good suggestion. We've looked at various heuristics, including looking at the max prefix lengths that we provision as a way to decide what is the right limit. We're just a little worried about putting an artificial limit on the IRR data because acquisitions happen, new customer gets onboarded, all of a sudden the number of routes goes up and we have the wrong list. But yeah, these are interesting challenges. I think we're still working through some of it.
For sure. In my experience, at least going off of effectively what you're receiving is a lot better data than what could be published on like PeeringDB for suggested limits. Last but not least, I'm just as much of a fan of progressive rollout of changes, but you mentioned like at least for your IRR filters, it can take potentially days to update the entire network. I'm curious if you're aggregating the prefix data that you're getting from the IRRs and doing or longer matching on that. Because if you were doing exact, it effectively sounds like it could take days for Google to accept one of my more specifics that.
We do use the or longer. There's some challenges with it also because there's a little bit of discrepancy that does arise, but yeah, we have aggregated the lists to the extent that we can. It still takes days just because all of our fleet-wide rollouts are typically on that order. And there's some challenge with some peers expecting, hey, I made the IRR change, why are you guys still rejecting the route? And we have to explain, it's in progress of being rolled out. By this date, it should be in the network. Check back.
Thank you.
Thank you.
Michael Costello, no corporate affiliation. I'm really glad that you touched on moving away from route servers. And I'd love to talk to you more about it later, but I'm wondering if you think generally route servers, there's something inherently insecure about it, or there's something particular about Google's peering mix that makes it problematic?
So I'm not an expert, but my sense from talking to the people who are experts in the company is that I don't know there's anything inherent. I think the problem is we don't really have a accepted best practice in how things like AS sets are defined or how the route server AS is propagated to us such that we could build a filter, for the actual networks behind it versus on the peer, who looks like either the route server in some cases, in other cases it's the peer directly. I think it's just the lack of that uniformity. I have to give credit, lots of IXPs do their own route validation that we can leverage. But we're also a bit nervous about outsourcing our security to third parties. We want to be able to do that validation ourselves as well, and it's challenging with route servers. I think that's been the main motivation.
And also, you were talking about this rollout and having to come up with rules and relax them and how difficult it is. Isn't this something that AI could just do for you?
Yeah,
you don't need to answer it if you don't.
Oh, so I will say that we have done projects. These are like exploratory projects looking at just whether AI can just detect invalid routes for us at the edge. It's not easy, right? I think the challenge that I see is that the training set is just too small to teach AI what is an invalid or valid route. So we can get reasonably good precision with lousy recall, basically, on the experiments that we did. Granted, we didn't spend a ton of time on it, but the initial experiments show that there's more work to be done there.
Thank you so much, Anis.
Thanks.
Hi, Chandler Willoughby, Bandwidth. So you mentioned as part of your traffic safety that you're monitoring the amount of traffic coming from specific prefixes. Perhaps an ignorant point of view, but I would imagine at Google scale that probably gets really expensive if you're doing flow tracking on a per peer basis. Are you doing flow tracking on a per peer basis, or is there some other technology you're using to monitor traffic from specific prefixes?
We have a very large scale system that looks at all the traffic that we get on every prefix from every peer.
Fair enough. Thank you.
Thanks.
Christophe, YXCIX. Probably many people can answer that, but I was just wondering, when you do BYOP, bring your own IP, why don't you just add them to the AS path? Why do you do still why does it originate from your network?
Oh, I mean, they most of these customers, with this two variants to this bring your own thing, customers can bring their own ASN as well, and sort of they can originate the routes from their own ASN. But the starting point for most of these services is they just bring their routes, and they are just published from Google Cloud and originated from us. So they have to create ROAs that authorize us. It's not uncommon. I mean, there's lots of multiple origin prefixes out there. BYOP is just another instance that a lot of cloud service providers are supporting. And there's a few use cases. I didn't have time to go through all the specific use cases, but lots of security services use this, VPN services use this, those kinds of things.
Thank you. Appreciate it.
All right. Thank you, Anish, for a very interesting talk.